Tonight, we're going back to the beginning of the dinosaurs, not to the age when giants ruled, not yet. Tonight we go further back, to the slow and extraordinary morning of their story, to the moment before the thunder of their footsteps shook the land, to the age of chaos and fire and strange quiet creatures who had not yet become the rulers of the world, to a time when the earth was still deciding what it wanted to be. This is the Age of Reptiles. This is the rise of the dinosaurs. Settle in now. Let your body grow heavy and still. Let your breathing slow. Let the sounds of your world fade gently into the background. There is nothing to do tonight. Nowhere to be. Nothing to carry. All of it can wait. Tonight, you're simply a traveller through deep time, drifting backward through hundreds of millions of years, carried gently by the quiet current of an ancient story. Let us begin. If you enjoy listening to sleepy prehistoric dinosaur stories like this, subscribe. I post stories like this weekly. To understand the rise of the dinosaurs, we must first understand the world they were born into, and that world was not gentle. It was not welcoming. It was a world that had just recently nearly ended. Travel back with me now. Not 66 million years, not 100 million years, much further, 252 million years ago. The Earth looks nothing like the planet you know. There is only one great landmass. Scientists call it Pangaea, which means something like all the land. Every continent you have ever seen on a map, every mountain range, every river valley, every desert and jungle and polar shore, all of it pressed together into one enormous supercontinent, surrounded by a single vast ocean called Panthalassa. The world breathes as one body. The land breathes as one body. Everything is connected. But something has gone wrong. Something has gone terribly, catastrophically, almost finally wrong. Somewhere deep in what is now the region of Siberia, the crust of the Earth has cracked open. Not in the way a fault line shifts and rumbles. This is different. This is the kind of rupture that rewrites the planet. Vast rivers of molten rock pour up through the crust and spread across the surface, covering an area larger than modern-day Europe. The lava does not stop for days. It does not stop for months. It does not stop for tens of thousands of years. It continues for nearly 1 million years, flooding the landscape in layer after layer of dark basalt, releasing enormous volumes of carbon dioxide and sulfur and methane into the atmosphere. The air changes. The oceans change. The temperature of the planet climbs. Then the chemistry of the ocean shifts, turning acidic, suffocating marine life. The oxygen in the water drops. Coral reefs collapse. Fish die in vast schools, marine reptiles vanish, and on land the forests thin and wither, the insects fail, and the creatures that had dominated the world for millions of years begin to disappear one by one, species by species, family by family, until the silence spreads across the whole of the Earth. This is the Permian-Triassic extinction event. Scientists sometimes call it simply the Great Dying. It is the worst mass extinction in the history of complex life on this planet. When it is over, more than 90% of all marine species have been erased. More than 70% of all land-dwelling vertebrate species are gone. Insects, which had never before experienced a mass extinction, suffer their own losses. The Earth is nearly emptied. The world that remains is barren, scarred, sooty and strange. Vast regions of the supercontinent are little more than red desert. The forests, once lush and green, are replaced in many places by a ghostly landscape of dead wood and wind-blown sediment. Fossils from this time contain almost nothing. The boundary in the rock record is stark and silent, a line where life simply stops. For millions of years after the Great Dying, the Earth is quiet. Not the warm and teeming quiet of a healthy forest at midnight, but the cold and empty quiet of a world that has lost most of itself. The sun rises every morning over a landscape that is pale and still. The seas are warmer than they should be. The seasons are extreme. Rains come in fierce sudden storms, then vanish entirely, leaving the red earth cracked and baked. Only the hardiest organisms survive. Bacteria, fungi, a few small reptiles, insects that have found ways to endure what nothing else could endure. But life is patient. Life is stubborn in ways that no catastrophe can fully extinguish. And slowly, in the deep corners of the world, in burrows and beneath rocks and at the edges of rivers, something begins to stir. The survivors begin to multiply. The early Triassic period is the age of recovery. It lasts roughly 5 million years, which sounds like a long time, but in the context of Earth's 4.5 billion year history, it is barely a breath. During these 5 million years, life does not simply recover quietly, it reinvents itself. The niches that have been emptied by the extinction are like blank pages waiting to be written on. Any creature that can survive, any creature that is flexible enough and hardy enough and adaptable enough, has an extraordinary opportunity. The survivors inherit a world of open space. Among those survivors are the archosaurs. The word archosaur means ruling reptile, which is fitting, because the archosaurs are the ancestors of everything we are interested in tonight. They are not yet dinosaurs. They are not yet crocodilians. They are not yet birds. But they carry within their bodies the blueprint, the ancient template from which all of these lineages will eventually emerge. Early archosaurs look something like a cross between a lizard and a crocodile. Their legs spread out to the sides of their bodies the way a modern lizard's legs do, rather than being held directly beneath the torso. They are generally small, modest, built low to the ground, but they are efficient, they are adaptable, and they are spreading. As the Triassic period progresses and the world slowly recovers from the Great Dying, the archosaurs begin to diversify. Different lineages develop different strategies. Some grow large and become powerful predators. Others become herbivores, processing the slowly returning vegetation. Some begin to experiment with walking more upright, their legs shifting from the sprawling posture of lizards toward the more erect posture that will eventually define the dinosaurs. Picture the Triassic world as it slowly comes back to life. The supercontinent of Pangaea is still largely intact, though its edges are beginning to crack. The climate is hot and dry across most of the interior, with harsh desert conditions that few animals can tolerate. But along the coasts, and in the river valleys, and near the wet tropical zones close to the equator, life is finding purchase. Ferns spread across the ground. Seed-bearing plants called cycads grow in dense clusters, their thick trunks and dark green fronds filling the air with a strange prehistoric scent. Conifer trees rise in forests that are nothing like modern pines or firs, but share the same ancient lineage. The world is greening again, slowly, tentatively, but greening nonetheless. And into this world of recovery and possibility, moving quietly through the undergrowth, eating insects and small reptiles darting from shadow to shadow, come the earliest ancestors of the dinosaurs. They are small. You might not notice them if you passed by. You might mistake them for lizards, or for any number of the other small reptiles that share their world. But look more carefully. Look at the way they hold their legs, not splayed outward like a crocodile, tucked more directly beneath the body. They are standing a little more upright than their relatives. They are moving a little differently, running on two legs sometimes, which is unusual, which is new, which is the beginning of something the world has never seen before. The first tentative steps of the dinosaurian lineage are being taken. Softly, quietly, in the green shadows of a recovering world, the dynasty of the dinosaurs is beginning to dawn. Let that thought settle over you as gently as a warm night settling over a summer field. The world had nearly ended, and from that almost ending something extraordinary began to grow. The Triassic period lasts for approximately 51 million years, stretching from roughly 252 million years ago to around 201 million years ago. It is divided by scientists into three broad intervals: the early Triassic, the middle Triassic, and the late Triassic. Each of these intervals sees the world change in significant and sometimes dramatic ways, and each plays a role in the story of how dinosaurs went from being small, inconspicuous survivors to the dominant animals on land. Allow yourself to sink a little deeper now. Let the weight of your body settle into the surface beneath you. Let your muscles release their last traces of tension. The day is gone, the night is quiet, and the story continues. The early Triassic, as we have already visited, is the period of recovery. It is a world dominated by survivors, by opportunists, by generalists who can eat almost anything and tolerate almost any conditions. The dominant land animals during this period are not archosaurs and certainly not dinosaurs. They're a group of creatures called therapsids, sometimes called the mammal-like reptiles, which despite their name are neither fully mammalian nor simply reptilian. They are something in between, a fascinating branch of vertebrate life that had been among the dominant animals of the Permian world and had somehow pulled through the extinction with enough survivors to rebuild. The most common of these Triassic therapsids is a creature called Lystrosaurus, a stocky, barrel-bodied herbivore about the size of a large dog. Lystrosaurus is not glamorous. It is not remarkable in the way that great predators or giants are remarkable. But it is tough. Fossils of Lystrosaurus have been found on every continent, including Antarctica, which at the time was part of the supercontinent and had a much warmer climate. Its ability to survive the harshest conditions of the aftermath, to thrive in a world of thin soils and sparse vegetation, makes it one of the most successful animals of its time. In some fossil beds from the early Triassic, remains of Lystrosaurus make up an astonishing 95% or more of all vertebrate fossils found. This is a world so thoroughly dominated by a single genus that the diversity of life, the rich tapestry of forms and strategies that had existed before the extinction, has not yet been restored. But as the Middle Triassic arrives, the world warms and diversifies. The supercontinent is still largely intact, but the recovery of ecosystems is accelerating. New groups of archosaurs appear and spread. The most important split in archosaur evolution occurs during this time. On one side of the family tree we find the pseudosuchians, the ancestors of modern crocodilians. On the other side we find the ornithodyrans, the branch that will eventually give rise to both pterosaurs and dinosaurs. This split is one of the great turning points in the history of life on land, though at the time nothing about it would have seemed remarkable to any observer. The two groups of archosaurs are competing for resources, evolving different strategies, diversifying into different ecological roles. The pseudosuchians, with their sprawling or semi-erect postures, are initially quite successful. Some of them become large armoured predators, others become herbivores of considerable size. For a significant portion of the Triassic, the pseudosuchians are arguably the more dominant and diverse group, but the ornithodyrans have something going for them, a different posture, a different way of moving through the world. Rather than the sprawling limb posture of many archosaurs, the ornithodyrans are developing a more fully erect stance, their legs held directly beneath the body. This change may sound subtle, but its implications are profound. An erect posture allows for longer strides and greater speed. It allows for more efficient breathing during movement, because the muscles that expand the rib cage are no longer being used simultaneously to support the weight of the body. It allows for the development of bipedalism, moving on two legs, which frees the forelimbs for other functions. It allows, in short, for the kind of active, energetic, fast-moving lifestyle that will define the dinosaurs in their prime. Among the earliest members of the ornithodyran lineage are the lagopetids and the pterosaur precursors, small animals that fill the middle to late Triassic world with a new kind of movement. But the most significant development occurs in the late Triassic, around 230 to 240 million years ago, when the first true dinosaurs appear. The climate of the late Triassic is, in many regions, brutal. The interior of the supercontinent is a vast and largely uninhabitable desert, blasted by extreme heat and almost entirely without rain for months at a time. Near the coasts and in the tropical belt, monsoon rains bring temporary relief, but the overall picture is one of aridity and harshness. Seasonal variations are extreme. There are wet seasons and dry seasons, and the transition between them is often abrupt and violent. It is in this challenging environment that the dinosaurs are born. The earliest definitive dinosaurs come from two main regions where fossils have been found. In modern-day South America, particularly in what is now Argentina, and in modern-day Africa, particularly Tanzania. The Ishigualasto Formation in Argentina has yielded some of the oldest and most complete early dinosaur fossils, and it is from this red desert landscape that we get our best picture of what the world looked like when the dinosaurs first arrived. The Ishigualasto Formation preserves a world that looks something like a modern desert with rivers. Red and grey sediments tell the story of seasonal flooding, with rivers swelling and spreading during the wet season and retreating to almost nothing during the dry. Conifer trees and seed ferns grow in thickets near the rivers. Ferns and horsetails carpet the ground. The air is alive with insects. And moving through this landscape is a rich community of animals, most of which are not dinosaurs at all. Among the non-dinosaurian animals of the Ishigualasto Formation are several kinds of rhynchosaurs, barrel-bodied herbivores that chew tough vegetation with specialized teeth. There are cynodonts, small furry-looking animals that are close relatives of the ancestors of mammals. There are several species of pseudosuchian archosaurs, including predators that can reach several meters in length. And tucked into this community, small and easily overlooked, are the earliest dinosaurs. One of these earliest dinosaurs is called Eoraptor lunensis, which means dawn thief of the valley. It is a small creature, roughly the size of a Labrador retriever, lightly built with hollow bones and a somewhat bipedal posture. It has small, sharp teeth, suggesting it may have been an omnivore, eating both plants and small animals depending on what was available. It is not a towering predator. It does not yet rule anything. It is simply another small archosaur in a world full of archosaurs, doing its best to survive in a hot and difficult landscape. Another early dinosaur from this same formation is Herrerasaurus, a more dedicated predator, longer and more powerfully built than Eoraptor, with sharp, recurved teeth designed for gripping and tearing flesh. Herrerasaurus could reach nearly 3 meters in length, which would have made it a respectable predator in the late Triassic community, though still far from the giants that would come hundreds of millions of years later. And there is Eodromaeus, the dawn runner, a slender and agile bipedal predator that may represent one of the earliest members of the theropod lineage, the branch of dinosaurs that will eventually give rise to Tyrannosaurus rex and Velociraptor and every modern bird. These earliest dinosaurs are remarkable not because of their size or their power or their fearsome weapons, but because of what they represent. They are the beginning of something that will last for over 160 million years. They are the first sentence of the longest story in the history of land animals, and the world does not yet know what it has. Let the quiet of that thought hold you for a moment. The world in which the dinosaurs were born did not know what it was witnessing. The red deserts and the sparse forests and the river valleys of the late Triassic had no sense that the small, quick, upright creatures moving through the shadows would one day fill every ecosystem on every continent, that they would grow to sizes beyond comprehension, that they would develop feathers and crests and horns and clubs and teeth by the hundreds, that they would build societies and migrate across continents and fill the air with their calls. In the beginning, they were simply survivors, small and quick and alive in a difficult world, and that was enough. Close your eyes a little more fully now. Let the images come of their own accord, softly and without effort. Imagine the late Triassic landscape of South America. The evening is coming on. The sky above the Isigualasto Basin is a deep red and ochre as the sun descends behind the ridge of ancient hills. The heat of the day is beginning to release itself from the red desert floor. A warm wind moves through the seed ferns along the riverbank. In the distance, a group of rhynchosaurs graze quietly among the cycads, their flat teeth grinding the tough vegetation with a slow and steady rhythm. Near the river's edge, a small creature moves cautiously. It is bipedal, running on 2 legs, its forelimbs held up and forward. It is no longer than a meter from snout to tail. Its eyes are large and dark, alert to movement in every direction. Its bones are hollow, making it lighter and faster than its size might suggest. This is Eoraptor. This is the dawn thief. And it is hunting, if hunting is the right word for the quick, opportunistic foraging of a small omnivore. It pauses at the water's edge, drinks, then darts sideways after a beetle that has wandered too close, misses it, stands still for a moment watching the river flow past in the last light of the evening. It does not know that it is a dinosaur. It does not know that it is the beginning of a dynasty. It is simply alive, which is, in the history of the world, always enough. The earliest dinosaurs fall into 2 main groups, based on the structure of their hips. This distinction was recognized by the Victorian scientist Harry Seeley in 1887, and it remains one of the fundamental organizing principles of dinosaur classification. The 2 groups are the Saurischians, meaning lizard-hipped, and the Ornithischians, meaning bird-hipped. Somewhat confusingly, birds are actually descended from the lizard-hipped group rather than the bird-hipped group, which is one of those wonderful ironies that the history of life enjoys producing. The Saurischians include 2 major lineages: the theropods, which are bipedal predators that include everything from small agile hunters to enormous apex predators, and which also give rise to birds, and the sauropodomorphs, which include the long-necked giants, the true titans of the dinosaur world, the sauropods, as well as their earlier and somewhat smaller relatives. The Ornithischians include a vast array of herbivorous dinosaurs, among them the horned ceratopsians, the armored ankylosaurs, the plated stegosaurs, the dome-headed pachycephalosaurs, and the duck-billed hadrosaurs. Nearly all ornithischians are herbivores, and they will eventually become among the most diverse and successful plant-eating animals the world has ever seen. But in the late Triassic, none of this diversity has yet emerged. The earliest dinosaurs are all relatively small, generalized, and ecologically modest. They share their world with many other groups of archosaurs, some of which are initially more successful and more diverse. The pseudosuchians, the crocodile-line archosaurs, are particularly impressive during the late Triassic, filling large predatory niches that dinosaurs have not yet claimed. So what gives the dinosaurs their eventual edge? This is one of the most interesting questions in paleontology. For a long time, scientists assumed that dinosaurs must have had some fundamental biological advantage over their competitors from the very beginning, that their erect posture or their metabolic rate or some other feature made them inherently superior. But more recent thinking suggests that the story is more complicated and more interesting than that. For much of the late Triassic, dinosaurs and pseudosuchians coexist and compete, without either group decisively outcompeting the other. Dinosaurs are not yet dominant. They are simply present, one group among many in the rich and varied communities of the late Triassic world. They survive and diversify slowly, filling niches as they become available, adapting to local conditions, experimenting with new forms. And then something happens. Another mass extinction. The end Triassic extinction event, which occurs approximately 201 million years ago, is less severe than the Great Dying, but it is still devastating. It wipes out most of the pseudosuchians, eliminating the dinosaurs' main competitors on land. It eliminates many of the other archosaur groups that have been sharing the world with the earliest dinosaurs. It clears the stage, once again, of most of its major players, and when the dust settles, and when the volcanic eruptions that triggered the extinction finally quiet down, and when the world begins its slow recovery, the dinosaurs are still there. They have survived again. They have endured again. And this time, the world they inherit is largely empty of competitors. The early Jurassic period, which begins immediately after the end Triassic extinction, is the moment when the dinosaurs begin to truly rise. The supercontinent is beginning to fragment, cracks spreading through Pangaea as tectonic forces slowly pull it apart. The Atlantic Ocean is beginning to open, a thin strip of shallow sea widening between what will become Africa and the Americas. The climate is still warm, still largely dry in the interior, but the edges of the breaking continent are rich with life. And into this world of fresh opportunity, the dinosaurs begin to diversify in earnest. Theropods spread and grow. Some become large apex predators, replacing the pseudosuchian predators that have gone extinct. Others remain small and agile, filling niches for swift medium-sized hunters. The sauropodomorphs, the ancestors of the long-necked giants, begin to increase dramatically in size, browsing high vegetation that other animals cannot reach. The ornithischians, which have been relatively modest up to this point, begin their own radiation, developing new body forms and strategies. The world is theirs now, not by conquest, not by war, but by endurance, by surviving what nothing else could survive, by being there when the door opened. The first dinosaurs came into a world of fire and dry wind and red desert. They were small and quick, and nothing about them announced greatness, but they endured, and endurance, in the slow mathematics of evolution, is everything. Let your breathing deepen now. Let the story carry you forward, gentle as a current, slow as the drift of continents. There is something deeply peaceful about endings that contain beginnings. The way a winter field, bare and still and covered in frost, holds within its frozen soil the seeds of spring. The way a night sky, dark and silent, is also full of light travelling toward you from stars so distant that the light set out before the earth was born. Endings and beginnings are not opposites. They are the same motion, seen from different angles. The end of the Triassic period is exactly this kind of thing. 201 million years ago, the world is experiencing its third great convulsion in 50 million years. Deep beneath the surface, where the supercontinent is beginning to pull apart along its great central rift, magma wells upward, and once again the Earth bleeds fire. The eruptions that mark the end of the Triassic are called the Central Atlantic Magmatic Province events, and they are enormous. Hundreds of thousands of cubic kilometers of lava pour out over what will eventually become the edges of the Atlantic Ocean, covering enormous swaths of territory and flood basalts that look dark and final in the ancient landscape. The gases released by these eruptions, carbon dioxide and sulfur dioxide and methane and others, flood the atmosphere. The climate lurches, temperatures rise. Then the sudden darkening of volcanic haze may cause temperatures to plummet. The oceans acidify once more. Coral reefs collapse. Marine creatures die in vast numbers. And on land, the extinction ripples outward through food chains, taking down species that cannot adapt quickly enough. It is a hard time, but the dinosaurs endure it. Why do the dinosaurs survive the end Triassic extinction while so many of their competitors do not? There is no single clean answer, and this is one of the things that makes the history of life so genuinely interesting. Science does not always offer simple stories. It offers complicated, beautiful, unfinished ones. Part of the answer may lie in geography. The earliest dinosaurs are concentrated in the southern part of the supercontinent, in regions that may have been somewhat buffered from the worst effects of the northern volcanic eruptions. Part of the answer may lie in physiology. There is growing evidence that dinosaurs, or at least some lineages of dinosaurs, had metabolic rates and respiratory efficiencies that allowed them to handle environmental stress better than some of their competitors. Part of the answer may simply be chance. In any mass extinction, luck plays a role. Being in the right place at the right moment, having the right diet, having the right body size, having the right habits, these things can make the difference between survival and disappearance, regardless of any inherent superiority. What we know with certainty is this. When the early Jurassic begins, the dinosaurs are there, and most of their competitors are not. The Jurassic period stretches from approximately 201 million years ago to approximately 145 million years ago, a span of 56 million years. It is named for the Jura Mountains of Switzerland and France, where some of the first fossils from this period were studied by European scientists in the 19th century. In the popular imagination, the Jurassic is the dinosaur period, the time of the great sauropods and the large theropods, the time when the Age of Reptiles reaches its spectacular maturity. And that imagination is not wrong. The early Jurassic is still a world in recovery and transition. The supercontinent is fragmenting. Rifts are widening. Shallow seas are beginning to spread across low-lying portions of the continent, creating new coastal and wetland environments. The climate is warm and becoming increasingly humid in many regions, as the opening of the Proto-Atlantic allows moisture to penetrate further inland. Forests of conifers and cycads and ginkgos spread across the landscape, providing habitat and food for an expanding range of plant-eating dinosaurs. Among the early Jurassic dinosaurs, one of the most significant and fascinating groups is the prosauropods, sometimes called plateosaurs, or more broadly the early sauropodomorphs. These are large herbivores that are experimenting with something remarkable: size. Where the late Triassic dinosaurs had been mostly small, the prosauropods of the early Jurassic are growing larger. Some species reach lengths of 8 or 9 meters, dwarfing almost everything else on land. They are not yet the colossal sauropods of the late Jurassic, but they are pointing clearly in that direction. One of the most impressive early Jurassic dinosaurs is Mesospondylus, whose fossils have been found across southern Africa and which represents one of the most complete pictures we have of what early dinosaur life looked like. Mesospondylus is a prosauropod, a relatively long-necked herbivore that walks primarily on 4 legs, but can occasionally rear up on its hind limbs to reach higher vegetation. Its head is small relative to its body. Its neck is moderately long. Its gut is capacious, a sign of a herbivore that has to process large quantities of plant material. Fossils of Mesospondylus have yielded one of the most extraordinary discoveries in early Jurassic paleontology. Nests, complete nests, with eggs, with embryos preserved inside, and in one remarkable case, with evidence of the nesting site being used repeatedly over multiple seasons. These nests tell us that Mesospondylus was not simply laying eggs and walking away. It was returning to the same places to nest again and again, much as sea turtles return to the same beaches today. And the embryos preserved within the eggs tell us something even more intimate about the lives of these animals. The embryos of Mesospondylus show something surprising. Their front legs are relatively underdeveloped compared to their back legs. This suggests that when they hatched, they were probably not yet capable of walking on 4 legs, much less foraging for themselves. The hatchlings were likely relatively helpless, dependent on the adults for at least some period after hatching. This is parental care. This is nurturing, in an animal that lived nearly 200 million years ago. The early Jurassic world is also the time when theropods, the predatory dinosaurs, begin their own expansion. Several lineages of early theropods spread across the fragmenting supercontinent, adapting to different sizes and ecological roles. Some, like colossal, which is known from enormous bone beds in the American Southwest, are small and agile pack animals that may have hunted cooperatively. Others are growing larger, filling the top predator roles left vacant by the extinction of the pseudosuchians. And high above the dinosaurs, something else is happening, something entirely new. The pterosaurs, the flying reptiles, are taking to the air. Pterosaurs are not dinosaurs. They are a sister group to the dinosaurs, both lineages having diverged from a common ancestor within the ornithodyrran branch of archosaurs. But they share the dinosaurs' world, and their story is deeply intertwined with the rise of the dinosaurian dynasty. The earliest pterosaurs appear in the late Triassic, and by the early Jurassic they are becoming increasingly diverse and widespread. These earliest pterosaurs are small and bat-like in many ways, with long flexible tails and membranous wings stretched between elongated fourth fingers and the side of the body. They have teeth in their jaws, which distinguishes them from modern birds, and their bones are phenomenally light, the hollow architecture of flight taken to an extreme. Imagine standing on the shoreline of a Jurassic sea and looking up to see a pterosaur gliding past overhead. Its wings are pale and translucent in the sunlight. Its body is perhaps the size of a large crow. It tilts on a current of wind, adjusts effortlessly, and banks away over the water, scanning the surface for fish. There is a strange familiarity to it, something that reminds you of a seabird, even though it is neither bird nor bat but something older and stranger than either. The skies are no longer empty. The seas are filling with new life. The land is greening and diversifying. The dinosaurs are growing and spreading. The Jurassic dawn is arriving, and it is beautiful. Let the night hold you softly now. Breathe in the cool stillness of wherever you are. Let your thoughts slow. Let the day's concerns dissolve like mist in the morning sun. You are nowhere but here, and here is a very gentle place to be. By the Middle Jurassic, the world has transformed beyond recognition from the red deserts and sparse fern fields of the late Triassic. Pangaea is now well into its long fragmentation. The northern portion, which scientists call Laurasia, is beginning to separate from the southern portion, Gondwana. Shallow seas spread across lowlands, creating new coastlines and wetland environments. The climate is warm and humid across many regions, and forests of tall conifers and cycads and ginkgos stretch across vast areas of the newly diversifying landscape. Into this greening world come the great sauropods. If you ask most people to picture a dinosaur, they will likely describe something that is, at its heart, a sauropod. An enormous animal with a long neck, a long tail, a massive body, and 4 pillar-like legs. This is the archetypal image of the dinosaur, and it is not wrong. The sauropods are among the most extraordinary animals that have ever lived on this planet, and their rise to dominance is one of the most remarkable stories in the history of vertebrate life. Sauropods evolved from the prosauropod lineage of the early Jurassic. The transition from a creature like Massospondylus, which is large by dinosaurian standards, but still relatively modest in the broader context of life on Earth, to the true sauropods of the Middle and Late Jurassic, involves one of the most dramatic evolutionary progressions in size that the fossil record has preserved. In the span of perhaps 20 to 30 million years, the ancestors of the great sauropods grow from animals the size of large horses to animals the size of buildings. The secret to this extraordinary growth lies in a combination of features that work together with remarkable synergy. Hollow bones reduce the weight of the skeleton without sacrificing structural strength. Air sac systems, connected to the lungs, allow highly efficient one-way airflow that fuels the enormous metabolic demands of giant warm-blooded bodies. Extremely long necks allow the animals to access vegetation across wide areas without moving their enormous bodies, reducing the energetic cost of feeding. And a reproductive strategy based on laying many relatively small eggs, combined with rapid early growth, allows juveniles to move quickly past the most vulnerable stages of life. The result is an animal that seems to violate the intuitive laws of biological possibility, an animal that can grow to 100 feet in length, an animal that can weigh 70 tons or more, an animal whose neck alone is longer than most of the other land animals sharing its ecosystem, an animal whose footsteps leave impressions that persist for millions of years in stone. Among the great sauropods of the Middle to Late Jurassic, several deserve particular attention. Diplodocus is perhaps the most familiar, a long and slender sauropod from late Jurassic North America that stretched to perhaps 25 meters or more in length, most of it neck and tail. Diplodocus is elegant in its proportions, if an animal this size can be called elegant. Its neck is held roughly horizontal, sweeping from side to side as it feeds on low-growing vegetation, a living vacuum hose drawing sustenance from the landscape with extraordinary efficiency. Its tail is extraordinarily long and whip-like, and some scientists believe it could have been cracked like a bullwhip, producing sounds that carry for miles across the Jurassic plains. Whether this was for defense, communication, or courtship remains debated, but the image of a herd of Diplodocus cracking their tails in unison across the floodplains of Morrison Formation North America is breathtaking. Brachiosaurus stands as the opposite in terms of posture. Where Diplodocus sweeps its neck horizontally, Brachiosaurus holds its neck nearly vertical, its front legs longer than its back legs, tilting its entire body forward and upward like a living crane. A Brachiosaurus could browse at heights that no other land animal could reach, its head stretching perhaps 9 or 10 meters above the ground. Standing beneath one would have been like standing at the base of a building that was also alive, that breathed and moved and regarded you with enormous and unreadable eyes. And then there is Argentinosaurus. Even among the sauropods, Argentinosaurus is exceptional. This Cretaceous titanosaur from South America is one of the largest land animals that has ever existed on this planet. Estimates of its length range from 30 to 40 meters. Estimates of its weight run to 70 or even 80 tons. A single vertebra from its backbone weighs more than an adult human. Its footsteps would have been felt through the ground at a considerable distance, a rhythmic percussion that would have announced its presence long before it came into view. How do you feed a body this size? How do you keep 70 tons of warm-blooded flesh alive and moving across a landscape? The answer lies in the extraordinary feeding efficiency of sauropod necks. By being able to sweep through large areas of vegetation without moving the enormous body, a sauropod can access far more food per unit of energy expended than any similarly sized animal with a shorter neck. The energy saved by standing still and using the neck as a feeding arm, rather than having to walk from plant to plant, is enormous. This is part of the reason why enormous size, counterintuitively, can be energetically advantageous for an herbivore in a rich environment. The sauropods are also benefiting from the extraordinary productivity of the Jurassic landscape. The warm and humid climate, the spreading forests, the rich coastal wetlands and floodplains, all of this provides a nearly inexhaustible supply of plant material for herbivores that are efficient enough to process it. The sauropods are efficient. They are astonishingly, extraordinarily efficient, and they grow to match the richness of their world. Imagine the late Jurassic floodplains of what is now the American West, the Morrison Formation landscape. You're standing on a gently rolling plain, covered in a mix of low ferns and cycads, and thickets of conifers, and ancient relatives of the sequoia. A river meanders across the floodplain, its banks green with dense vegetation. The air is warm and humid, and the sounds of insects fill every quiet moment with a constant comforting hum. And then you notice movement at the tree line on the far side of the river, long necks rising above the canopy. 1, then 3, then 6. A herd of Brachiosaurus is moving through the forest at the edge of the plain, browsing at heights that no other creature can access, their massive bodies moving with a slow and rocking grace that somehow feels inevitable, like watching something fundamental about the world express itself in flesh and bone. They do not hurry. They do not need to. Nothing in this world is going to tell them to hurry. They are the largest things in it. One of them turns its head toward the river, pausing to assess the distance. Then it begins walking forward, its footsteps pressing deep into the soft earth of the floodplain, leaving impressions that will still be visible as stone impressions 200 million years from now. Another follows, then another. They move through the water with calm confidence, their long necks held above the surface, their bodies barely slowing as the river rises around their chests. On the far bank they emerge dripping and calm, and the feeding continues. Let that image settle over you like the warmth of an afternoon sun. The world has rarely been as rich as the Jurassic. It has rarely produced life on quite this scale. Let your breathing continue slow and steady. Let the darkness behind your eyes become the warm, tree-filtered light of a Jurassic evening. You are perfectly safe. You are perfectly still. The stories come to you on their own, gentle as the first stars appearing above the tree line. While the great sauropods were growing to sizes that challenge comprehension, their world was not without danger. The Jurassic period is also the time when the theropods, the predatory dinosaurs, begin their own great expansion. And the story of the theropods is, in some ways, even more remarkable than the story of the sauropods, because it is a story that does not end with the extinction of the non-avian dinosaurs 66 million years ago. It ends with every bird that has ever sung in every tree in every garden in every part of the world. The theropods are characterized by a bipedal posture, walking exclusively on their hind legs, hollow bones, three-toed feet, and in most lineages relatively small forelimbs compared to the body. They are almost exclusively carnivorous in the Jurassic, though some lineages will develop herbivorous or omnivorous habits by the Cretaceous. Their skulls are generally long and narrow, equipped with serrated teeth designed for gripping and slicing flesh. Among the Jurassic theropods, Allosaurus stands as one of the most impressive and thoroughly studied. A large predator from late Jurassic North America, Allosaurus could reach 9 to 12 meters in length and weigh perhaps 2 tons. It is not yet Tyrannosaurus rex in terms of size or power, but it is an apex predator of its ecosystem, and its fossils are found in abundance in the Morrison Formation, alongside those of the sauropods it may have hunted. Allosaurus has a distinctive skull, deep and powerful, with large fenestrae, openings in the bone that reduce its weight without sacrificing structural strength. Its teeth are blade-like and serrated, designed not for crushing bone in the manner of T-Rex, but for slicing and tearing flesh in efficient, powerful strokes. Biomechanical studies of Allosaurus skulls suggest that it may have used a hunting technique sometimes called hatchet attack, driving its upper jaw down into prey with great force, using the head itself as the primary weapon rather than simply biting. Whether Allosaurus hunted alone or in groups is still debated. Some sites show multiple Allosaurus specimens associated with large sauropod bones, which could indicate group hunting. But it could equally reflect multiple scavengers drawn to the same carcass. The question remains open, as so many questions about dinosaur behavior remain open. Picture an encounter between Allosaurus and a herd of large sauropods on a Jurassic floodplain. The sauropods are feeding quietly near a river bend, their long necks sweeping through the low vegetation while the adults stand like pillars around the feeding juveniles. The Allosaurus is watching from a tree line perhaps 300 meters away. It is still. It has been watching for some time. Its eyes track the movement of a juvenile at the edge of the herd, one that has wandered slightly further from the adults than is wise. The Allosaurus does not move yet. It waits. It is patient in the way that only a hungry predator can be patient. And then the juvenile sauropod takes one more step away from the protective cluster of adults. The Allosaurus begins to move, low and fast, covering the distance with a fluid urgency that seems at odds with its 2-ton body. And the herd responds, the adults swinging their enormous necks and tails, the juveniles crowding back toward the center. In the end, the juvenile is not taken. The adults form too strong a barrier. The Allosaurus pulls up short, makes a feint, then wheels away into the forest. It will try again. Perhaps tomorrow. Perhaps tonight. Patience is the strategy of a predator that cannot afford to be injured in a failed attack. Better to wait for the right moment than to press an attack against the risk of a sauropod tail cracking down on a leg like a battering ram. Beyond Allosaurus, the Jurassic theropod fauna includes a rich variety of smaller and more specialized predators. Ceratosaurus, with its distinctive nasal horn and unusual for a theropod, a row of small osteoderms along its back. Megalosaurus, one of the first dinosaurs ever to be scientifically described, a large predator of early to middle Jurassic Europe. Torvosaurus, perhaps the largest predator of the late Jurassic, known from fossils in both North America and Portugal. And, among the smaller theropods, something new and extraordinary is beginning to develop. Feathers. The discovery that many theropods, particularly the coelurosaurs, which include velociraptors and their relatives, had feathers has been one of the most transformative insights in paleontology over the last 30 years. Exquisite fossils from the Yixian Formation of northeastern China, dating primarily to the early Cretaceous, but representing lineages that began diversifying in the late Jurassic, preserve feathers in extraordinary detail. Downy filamentous structures cover the body. More complex penniceous feathers develop on the arms and tail. Colours are preserved in some specimens through melanosome structures. The late Jurassic theropod Epidexipteryx has elongated ornamental tail feathers used for display. Anchiornis has wings on both its arms and its legs, making it effectively a 4-winged glider. and Archaeopteryx, discovered in the limestone quarries of Bavaria in the 19th century, and one of the most famous fossils in the history of science, has the teeth and claws and long bony tail of a dinosaur and the feathers and wings of a bird, straddling the boundary between two worlds with perfect anatomical honesty. These feathered theropods are telling a story. They are telling the story of how flight evolved, not as a sudden leap from the ground, but as a gradual process involving many intermediate stages. First feathers for insulation, for warmth in a small-bodied warm-blooded animal, then feathers for display, for communicating with members of the same species, then feathers on the arms, initially perhaps as aids to balance during running or leaping, then as gliding surfaces, then as true wings capable of powered flight. The exact sequence and the exact ecological context of this transition is still debated. Some paleontologists favour a ground-up model, in which running animals used feathered forelimbs to generate extra lift during leaps after prey. Others favour a trees-down model, in which gliding from trees gradually gave way to active flapping. Most likely the truth involves elements of both, with different lineages exploring different paths toward the same destination. What matters is this. By the end of the Jurassic, the theropod dinosaurs have sent a branch of their lineage into the sky. The first birds are in the trees, the first birds are in the air. The lineage that will one day produce hummingbirds and eagles and albatrosses and penguins has begun. The dinosaurs have not just conquered the land, they have learned to fly. Settle a little deeper now. Let the warmth of the night hold you. Let your thoughts drift freely, following the story wherever it leads, without effort, without urgency. The world of the Jurassic continues to unfold around you, endlessly rich, endlessly strange, endlessly generous with its wonders. We have visited the great sauropods, towering over the landscape. We have walked beside the theropods in their hunts and watched the first feathered cousins of the birds take to the air. Now let us turn our attention to the third great lineage of dinosaurs, the Ornithischians, whose story is quieter than that of the hunters and the giants, but no less extraordinary. The Ornithischians are, almost without exception, herbivores. Their name, bird-hipped, refers to the structure of their pelvis, in which the pubis bone points backward rather than forward as in the lizard-hipped Saurischians. This does not look particularly bird-like to modern eyes, but it is a fundamental anatomical distinction that places all the horned, armoured, plated and dome-headed dinosaurs on one side of the dinosaurian family tree. In the Jurassic period, the Ornithischians are still finding their way, diversifying into the ecological roles that the warming and greening world is opening up for large herbivores. One of the most notable Jurassic Ornithischians is Stegosaurus, an animal so distinctive that it has become one of the universal symbols of the dinosaur age. Stegosaurus is a large animal, reaching perhaps 9 meters in length and weighing up to 5 tons. It walks on 4 legs, low to the ground, with a characteristic arched back and a tail held above the ground. Along its back runs 2 alternating rows of tall, roughly triangular bony plates, each plate embedded in the skin rather than attached to the vertebrae. Their exact arrangement the subject of debate, but their visual impact unquestionable. And at the tip of its tail, 4 long, bony spikes, which paleontologists have given the affectionate informal name the thagomizer. The function of the plates has been the subject of considerable scientific discussion. Early theories emphasized their potential role in thermoregulation, with the large flat surfaces acting as solar panels to absorb heat in the morning and radiators to dissipate heat in the afternoon. More recent evidence suggests a primarily display function. The plates are richly vascularized, suggesting they may have been brightly colored in life, making Stegosaurus a visually dramatic animal that could signal its identity, health, and reproductive status to others of its species from a considerable distance. The tail spikes, by contrast, were clearly weapons. Fossil evidence of healed wounds in predatory theropods, injuries consistent with being struck by a Stegosaurus tail spike, tells us that these weapons were used and used effectively. A Stegosaurus defending itself against an Allosaurus would have been a formidable opponent, the heavy muscular tail capable of swinging the 4 sharp spikes with considerable force. Picture a Stegosaurus on a Jurassic afternoon, feeding on low ferns and cycads in a clearing. It moves slowly, deliberately, its plates catching the afternoon light and making it one of the most visually arresting animals in the ecosystem. A juvenile follows close behind, its own plate still small and soft, pressed against the adult's flank. The adult lifts its head and turns slightly, its small eye scanning the tree line where something has moved. Nothing emerges. The predator, if there was one, has decided against it. The Stegosaurus returns to feeding, its plates shifting almost imperceptibly in the light, the colours in them warm and vivid. Alongside the stegosaurs, the Jurassic ornithischians include the first ankylosaurs, the armoured dinosaurs that will eventually develop into the living fortresses of the Cretaceous, and the early ornithopods, bipedal or facultatively bipedal herbivores that represent the ancestors of the hadrosaurs. But the true explosion of ornithischian diversity is still ahead, in the Cretaceous period, when conditions and opportunities align to produce some of the most extraordinary forms in the history of vertebrate life. For now, in the Jurassic, the ornithischians are simply part of the rich tapestry of a dinosaurian world that is becoming more complex, more diverse, and more fully realised with every million years that passes. The world turns, the continents drift, the forests change, the seasons pass in rhythms older than memory, and the dinosaurs adapt to all of it. Let the gentleness of deep time settle over you now. You are warm, you are still. The night outside is quiet, and the story of the ancient world flows on like a river, steady and unhurried, carrying you forward without effort. The Cretaceous period, which extends from approximately 145 million years ago to 66 million years ago, is the longest and in many ways the most spectacular period of the Mesozoic era. It lasts for 79 million years, almost as long as the Jurassic and Triassic combined. It is the period in which the dinosaurs reach the full flowering of their evolutionary potential, producing forms of extraordinary diversity and complexity, occupying every ecological role available to large land animals, and doing so with such success that their fossils are found on every continent on Earth, including Antarctica. The Cretaceous world is fundamentally different from the Jurassic world. The fragmentation of Pangaea has progressed dramatically. North America and Europe are separated by the expanding North Atlantic. South America and Africa are pulling apart, the South Atlantic Ocean widening between them. India is an island continent, still millions of years from its eventual collision with Asia. Antarctica and Australia are still connected, still forming a southern landmass, with a warm temperate climate very different from the frozen continent we know today. These tectonic changes have profound consequences for the distribution and evolution of dinosaurs. As the continents separate, dinosaur populations that were once interconnected become isolated, evolving independently in their respective landmasses. North America develops its own distinctive dinosaur fauna, as does Asia, South America and Africa. The result is extraordinary. Biogeographic diversity, with different regions of the world hosting very different assemblages of dinosaurs. The Cretaceous is also the period of the great diversification of flowering plants. We have already touched on this in our earlier discussion, but it bears returning to because the rise of angiosperms is one of the most important ecological events of the Cretaceous, transforming landscapes and food webs and ultimately influencing the evolution of dinosaurs in ways that are still being understood. Before the rise of flowering plants, the primary vegetation of the Mesozoic world consists of conifers, cycads, ferns, horsetails, and ginkgos. These are ancient, slow-growing plants that do not flower and do not produce fruits in the modern sense. They are nutritious enough, certainly, to support the enormous appetites of sauropods, but they do not offer the concentrated packages of nutrition that fruits and seeds represent. As angiosperms spread through the Cretaceous, they change the landscape. Broadleaf forests begin to appear in tropical and subtropical regions. Flowering understory plants spread through forest floors. Fruits appear, offering rich concentrated nutrition to any animal capable of consuming them. The diversity of plant life increases dramatically, and with it the diversity of the insects and other invertebrates that feed on and pollinate the flowers. This floral revolution creates new opportunities for herbivorous dinosaurs. The hadrosaurs, the duck-billed dinosaurs, evolved their extraordinary dental batteries precisely during this period of diversifying plant life, developing the ability to process a wide variety of tough plant materials more efficiently than almost any other herbivore. The ceratopsians, the horned dinosaurs, developed their parrot-like beaks and powerful jaw muscles to handle the tougher, low-growing vegetation of Cretaceous forests. Even some theropods develop plant-eating habits, taking advantage of the new abundance of energy-rich fruits and seeds. The Cretaceous is also the time of the great hadrosaur herds. Hadrosaurs, those most familiar of ornithischians, spread across the northern continents in vast numbers, their fossils abundant in every major Cretaceous dinosaur-bearing formation from the American West to Central Asia to Europe. These were social animals, living in herds whose size we can only partially estimate from trackways and bone beds, but which may have numbered in the hundreds or even thousands. The Parasaurolophus, with its extraordinary backward-sweeping hollow crest that could reach 6 feet in length, is perhaps the most evocative of the hadrosaurs. That crest is a resonating chamber, a biological instrument. The air passages within it, connecting the nasal cavity to the lungs, allowed the animal to produce deep, powerful calls that would have been heard at great distances. Computer reconstructions of Parasaurolophus skull acoustics suggest a sound somewhere between a foghorn and a French horn, deep and resonant and slightly haunting. Imagine a Cretaceous sunset over a broad floodplain in what is now the American West. A herd of Parasaurolophus, perhaps 40 or 50 animals, is moving across the plain toward a distant river, their footsteps making a low rhythmic percussion against the dry earth. And then one of them lifts its crested head and calls. The sound carries. It is low and round and beautiful in the way that all sounds carrying great distances are beautiful, the way foghorns are beautiful, the way thunder is beautiful. Another answers from somewhere in the middle of the herd, then another from the far right flank. The calls interweave and harmonize, filling the evening air with a chorus that has not been heard on this earth for 66 million years. The Cretaceous is the golden age of the dinosaurs. It is the period in which their long dynasty reaches its full expression, and it is also the last. The night grows deeper and quieter around you. Your breathing has slowed. The day's thoughts have drifted far away, replaced by the warm and distant shapes of an ancient world. Let them come as they will. Let them pass as they will. You are simply here, floating gently in the quiet current of the story. To truly understand the rise of the dinosaurs, we must spend some time not just with individual species or individual events, but with the texture of daily life in the dinosaurian world. Because the dinosaurs did not merely exist, they lived. They formed communities and societies, however alien those communities might seem to our eyes. They raised young and competed for mates. They navigated ecosystems of extraordinary complexity. They suffered injuries and recovered from them. They made mistakes and learned from them. They were, in every meaningful sense, living animals, as fully alive in their world as any creature alive today. Consider the daily life of a young hadrosaur, growing up in a nesting colony on the shores of a Cretaceous seaway. It hatches from an egg about the size of a large grapefruit, emerging into a world of warmth and activity and the constant presence of adults moving around the nest site. It is not alone. Its clutch mates are hatching alongside it, small and damp and blinking in the light. The nest is a broad, shallow depression in the sand, lined with plant material that has been composting to generate warmth, much as modern alligator nests are constructed. Above, a parent circles and watches, alert to any predator that might approach. For the first weeks of its life, the young hadrosaur stays close to the nest. Its legs are strengthening day by day, its muscles developing from the thin and uncertain things they were at hatching to something more capable of sustained movement. It feeds on soft plant material at first, the tender new growth that grows at the edge of the nesting area, supplemented perhaps by protein-rich insects that it catches in the vegetation around the nest. It grows quickly. This is essential. A small hadrosaur is vulnerable to an enormous range of predators, from small theropods that could take a hatchling with ease, to larger predators that might target juveniles. Every day it grows is a day it becomes slightly less vulnerable. Within a few months, the young hadrosaur is large enough and strong enough to move with the herd. It falls into the patterns of herd life with the ease of an animal that has evolved for precisely this: moving with others, staying close to larger adults, learning the routes to water and food that the herd follows season by season across its home range. The herd is a complex social entity. It is not simply a crowd of animals moving together for the convenience of numbers. It is a structured community with its own dynamics, its own hierarchies, its own communication. The large adults form the outer perimeter when danger threatens. Their great bodies a moving wall between the predators and the juveniles at the center. The various calls of the crested adults coordinate movement, alert the herd to threats, maintain contact across the wide spread of individuals, and there are always threats. The late Cretaceous ecosystems of North America are among the most predator-rich environments in the history of land life. The hadrosaurid herds share their world with Tyrannosaurus rex, with Albertosaurus and Daspletosaurus, and other large tyrannosaurs, with smaller theropods that are capable of taking juveniles and subadults. The herds are the hadrosaur's primary defense, the safety that numbers provide, the many watchful eyes that make approaching unseen almost impossible. Tyrannosaurus rex deserves a moment of its own in this story. It is perhaps the most famous animal in the history of paleontology, the apex predator of the late Cretaceous Hell Creek ecosystem, the absolute lord of its ecological niche. And it is far more interesting than popular culture has ever fully captured. T-Rex is enormous. An adult can reach 12 to 13 meters in length and weigh 8 to 9 tons. Its skull is massive, over a meter long in the largest specimens, with deep jaws equipped with serrated banana-shaped teeth that can reach a foot in length. Its bite force is the strongest of any land animal in the history of the Earth, estimated at 12,000 pounds per square inch or more. It can crush bone. It does crush bone. Fossilized hadrosaur and ceratopsid bones show deep tooth marks from T-Rex, marks that go all the way through the cortex and into the spongy bone beneath, evidence of a predator extracting every possible calorie from its prey. But T-Rex is not simply a machine for crushing bone. It is a sophisticated, complex animal, with a large brain relative to its body size, keen senses of smell and hearing, depth perception from forward-facing eyes that compares with many modern predatory birds. There is growing evidence that T-Rex may have been covered in some form of integumentary covering, whether scales, proto-feathers, or some combination of both, over at least portions of its body. The question of what T-Rex sounded like remains fascinating and open. Its closest living relatives, the crocodilians and the birds, do not roar in the way that movies portray. They produce a range of sounds from hisses to deep resonant calls to infrasonic vibrations. T-Rex most likely communicated through deep, chest-felt rumbles and infrasound, rather than the theatrical roar of cinema. Imagine standing still on a late Cretaceous floodplain at twilight. The light is failing. The hadrosaur herd that was visible on the far side of the river an hour ago has moved away. The air is still and heavy with the smell of mudflats and distant conifers, and then the ground begins to vibrate, very slightly, beneath your feet. Not from footsteps, not yet, from sound. A deep, penetrating vibration in the air and the earth, felt more than heard. The call of a Tyrannosaurus rex hunting in the failing light. You cannot see it. You cannot hear it in the conventional sense, but you can feel it everywhere, in your bones, in your chest. This is the experience the hadrosaurs lived with. Every day, in every season, the presence of the great predators was woven into the fabric of their existence, and they endured it by staying together, by moving in numbers, by calling to each other across the floodplain in their extraordinary resonant voices. The dinosaurian world was not simply a collection of impressive animals. It was an integrated web of relationships, of predator and prey, of parent and offspring, of competitor and symbiont. It was, in the truest and deepest sense of the word, a world rich and strange and wonderful beyond easy description. Let the quiet deepen further around you. You are drifting now, gently and surely, in the soft current between waking and sleep. The story continues, easy and unhurried, nothing demanding of you, nothing requiring effort. Simply the slow, beautiful panorama of an ancient world, and you moving through it like a cloud moves through summer sky. The Cretaceous period is also the time of some of the strangest and most wonderful dinosaur forms. Evolution, given enough time and enough ecological opportunity, explores directions that no reasonable prediction could have anticipated. And the Cretaceous is full of surprises. Spinosaurus, the largest known carnivorous dinosaur, longer than T-Rex at perhaps 14 to 15 meters, is one of the strangest of all large theropods. Unlike other large carnivorous dinosaurs, Spinosaurus does not appear to have been primarily a land hunter. Its skull is long and narrow and crocodilian, equipped with conical teeth rather than serrated blades, clearly adapted for catching fish. Its legs are short relative to its body, reducing its speed on land but suggesting a different primary lifestyle. Its bones are dense, more than those of other theropods, helping it sink in water rather than float. And along its back rises an enormous sail of tall neural spines, each perhaps 2 meters in height, forming a ridge of extraordinary visual impact. Spinosaurus was, in all likelihood, a semi-aquatic predator, hunting fish and other aquatic prey in the vast river systems of Cretaceous North Africa, much as a giant heron or a giant crocodile might hunt today. It may have waded in shallows, ambushing large fish that swam beneath the surface. It may have swum, using its muscular tail as a paddle. It represents a remarkable departure from the stereotype of the large theropod as a cursorial land predator, proof that the dinosaurian body plan was flexible enough to invade environments that nothing like it had occupied before. The ceratopsians, the horned dinosaurs, deserve their own particular moment of attention, because they are among the most visually extraordinary animals the Cretaceous produces. Triceratops, the most familiar, with its 3 horns and its great bony frill, is merely one member of a diverse family that includes dozens of species, each with its own unique configuration of horns, frill spines and frill patterns. Styracosaurus has a frill edged with long, forward-pointing spines, making its head look like an elaborate Baroque crown. Pachyrhinosaurus has a rough, bossed mass of bone on its snout instead of a nasal horn, giving it a strangely brutish and powerful look. Cosmoceratops has more horns than any other known animal, with 15 separate, horned projections on its skull and frill. Diabloceratops has 2 enormous backward-sweeping horns from its frill that make it look like an animal that belongs in mythology rather than paleontology. What are all these horns and frills for? Some of them are almost certainly weapons. The long brow horns of Triceratops, which can exceed a meter in length and which show signs of wear and combat damage in adult specimens, were almost certainly used in contest with rivals and in defense against predators. The image of a Triceratops lowering its head and presenting its 3 horns to a Tyrannosaurus rex is not pure fantasy. Fossil evidence shows both predatory engagement between these species, including T-Rex bite marks on ceratopsid bones, and healed injuries on Triceratops that are consistent with surviving predator encounters. But many ceratopsian horns and frill features are far too elaborate to be explained simply by weapons function. The ornate spines of Styracosaurus, the multiple projections of Cosmoceratops, these are clearly displays. They are signals. They are the ceratopsian equivalent of the peacock's tail, biological advertisements of genetic quality, visual demonstrations of dominance, instruments of species recognition, in a Cretaceous world that contained multiple ceratopsian species living in the same ecosystems. The hadrosaurs, too, are remarkable in their variety of crests and skull ornaments. We have already visited Parasaurolophus with its 6-foot backward-sweeping hollow crest, but it shares the Cretaceous with Lambeosaurus, whose crest is a tall hatchet-shaped structure rising above the skull, with Corythosaurus, whose crest forms a tall rounded helmet, with Hippacrosaurus, whose crest is intermediate between a helmet and a tube. Each of these crests is slightly different. Each of them acts as a different resonating chamber, producing a different sound. Scientists who have modelled the acoustics of these various crest types find that each species would have produced a distinctive call, a biological signature that would have allowed hadrosaurs to identify members of their own species from a great distance. In a world where dozens of species of large herbivores might coexist in the same landscape, this kind of acoustic species recognition would have been enormously valuable. You would know whether the animals approaching through the forest were your own kind, or something else, simply from the sound of their calls. Among the other remarkable Cretaceous forms are the pachycephalosaurs, the dome-headed dinosaurs, whose thick skull roofs, sometimes more than 10 inches of solid bone, were almost certainly used in headbutting contests. The therizinosaurids, bizarre theropods with enormous curved claws that gave up carnivory for herbivory, their long necks and gentle bodies making them look like something from another world. The alvarezsaurids, tiny specialized insectivores with one large digging claw and vestigial hand arms. The oviraptorosaurs with their parrot-like beaks and elaborate crests, whose name means egg thief but whose fossils tell a story of devoted parenthood. All of this diversity, all of this extraordinary range of forms and strategies and appearances developed within a single evolutionary lineage over the course of 160 million years. The rise of the dinosaurs was not a single event. It was an unfolding, a slow and magnificent flowering of biological possibility across geological time. And it was still going, still spreading and diversifying and finding new ways to be alive, right up until the moment the sky changed. The night is fully around you now, deep and warm and still. Your breathing is slow and even. The story of the ancient world drifts through you like music, gentle and continuous, asking nothing except that you let it flow. We have travelled a long way together tonight, from the red deserts of the late Triassic, where the first small dinosaurs moved cautiously through a world still recovering from near-total extinction, through the greening Middle Jurassic, where the great sauropods began their extraordinary experiment with size, through the golden age of the Jurassic, when theropods and ornithischians diversified into forms of extraordinary variety, and through the long and spectacular Cretaceous, the golden afternoon of the dinosaurian dynasty. Now let us slow down. Let us not rush to the end, because the story of the rise of the dinosaurs is not a story with a simple ending. It is a story with a transformation. The asteroid that struck the Earth 66 million years ago, at what is now the Yucatan Peninsula in Mexico, ended the reign of the non-avian dinosaurs with a swiftness that the geological record finds almost jarring. In the rocks below the boundary layer, the Cretaceous-Paleogene boundary, the fossils are rich and diverse. In the rocks above it, they are gone. Tyrannosaurs, ceratopsians, hadrosaurs, ankylosaurs, sauropods, the great lineages of non-avian dinosaurs simply vanish from the record with a completeness that speaks to the absolute nature of the catastrophe. The asteroid was approximately 10 to 15 kilometers in diameter. When it struck, it released energy equivalent to billions of nuclear weapons, triggering earthquakes, tsunamis, wildfires, and a global winter as the impact ejector and the soot from burning forests blocked sunlight for months to years. Without photosynthesis, plant life collapsed. Without plant life, the herbivores starved. Without herbivores, the predators followed. It is a story of cascading failure, of a world's ecology unwinding from the bottom up. And yet some survived. Among the survivors of the end Cretaceous extinction are the ancestors of all modern birds. Small, feathered, warm-blooded, flexible in their diets, capable of eating seeds and insects that persisted through the winter, capable of surviving on less because their metabolic efficiency was high. They endured the impact winter, they endured the collapse of forest ecosystems, and when the world recovered, they were there. And they had survived precisely because they were dinosaurs. Because the adaptations of the dinosaurian lineage, the hollow bones and the air sac systems and the warm-blooded physiology and the feathered insulation had made them capable of surviving conditions that no other large vertebrate group could withstand. The dinosaurs rose from the ashes of the Permian extinction. They survived the end Triassic extinction. They survived volcanic events and climate shifts and sea level changes and the fragmentation of continents across 166 million years. And when the asteroid came, they survived that too. Not all of them. Not the non-avian lineages, but the birds, the descendants of theropod dinosaurs, the living, flying, singing continuation of the most successful dynasty of land animals the world has ever seen. Think of this when you hear a bird outside your window. Think of the vast and ancient lineage it represents. Think of the red desert of the Triassic where the first small dinosaurs took their first cautious steps. Think of the Jurassic floodplain, where a herd of Diplodocus moved like slow mountains across the landscape. Think of the Cretaceous evening where a Parasaurolophus lifted its crested head and called across the floodplain in a voice like a foghorn wrapped in music. All of that is still here, changed beyond recognition, miniaturized, given wings and song, but here, undeniably, magnificently, stubbornly here. The rise of the dinosaurs did not end, it transformed. And in that transformation, the most ancient of living dynasties still moves among us, daily and quietly and everywhere. Every sparrow, every robin, every eagle soaring on a warm afternoon thermal above the hills, every hummingbird hovering at a flower, every albatross riding a southern ocean gale, every penguin sliding on the ice, all of them dinosaurs, all of them the living continuation of a story that began 240 million years ago in a recovering world, in a red desert with a small and quick and unimportant seeming creature that simply kept moving through the shadows. What endures is not always what was loudest or largest or most powerful in its moment. What endures is what is flexible, what is adaptable, what is willing to become something new when the old world ends and a new one begins. The dinosaurs endured, and they endure still. Let that thought be with you as you drift now, as the story settles gently into quiet, as the ancient world recedes and the warm dark of sleep comes forward to take its place. You have been walking with giants. You have been keeping company with the most successful animals in the history of life on land. Rest now. Stay with me now just a little longer. Let your body remain still and heavy. Let your breathing remain slow and even, because before we drift fully into the quiet, there is something more to tell. Something that the textbooks do not always say clearly. Something that the museum placards gloss over. Something that changes the entire shape of the story we have been telling tonight. Because we have been telling you the story of the rise of the dinosaurs, and that story is true, but it is not the whole truth. The whole truth is stranger. The whole truth is more surprising. The whole truth is, in some ways, more beautiful and more unsettling than the version most people carry in their minds. And tonight, in the deep and quiet hours, with your eyes closed and the world still around you, we are going to look at the whole truth together. There are things about the rise of the dinosaurs that science has only recently begun to understand. Things that were hidden in plain sight for decades, embedded in fossils that everyone had already found but had not yet fully read. Things that require a different kind of attention, a slower and more patient attention than the hunt for the biggest or the most dramatic specimen tends to allow. And when you see them, everything shifts. The story does not become less wonderful, it becomes more so. Let us begin the twist. The first thing you need to understand is this: the dinosaurs were not supposed to win. This is not a figure of speech. This is a genuine scientific insight that has emerged from careful study of the Triassic fossil record over the last 2 decades. For most of the late Triassic period, the dinosaurs were not the dominant animals on land. They were not even close to being the dominant animals on land. They shared their world with a rich and diverse community of other archosaurs, and for the first 20 to 30 million years of their existence, they were, by most ecological measures, relatively minor players. The pseudosuchians, the crocodile-line archosaurs that we mentioned earlier in our journey, were in many respects more impressive than the early dinosaurs. They were more diverse, they filled more ecological niches, they produced larger and more powerful forms, including apex predators that dwarfed anything the early dinosaurian lineage could offer. Some of them were enormous armoured herbivores, some were swift bipedal runners, some were heavily armoured tank-like creatures. They were, in the ecological language of the Triassic, the more successful group, and then the end-Triassic extinction happened, and the pseudosuchians were largely wiped out, and the dinosaurs were not. Here is the question that paleontologists have been struggling with ever since this pattern became clear. Why? Why did the dinosaurs survive the end-Triassic extinction, when so many of their apparently more successful competitors did not? What did the dinosaurs have that the pseudosuchians lacked? For a long time, the answer was assumed to be something inherent to the dinosaurian body plan: the erect posture, the more efficient breathing, the possibly higher metabolic rate. The popular version of the story, the one told in most textbooks and documentaries, is that the dinosaurs won because they were simply better animals, more efficient, more active, more adaptable, superior. But recent research has begun to challenge this narrative in a very interesting way. A landmark study published in the early 21st century examined the pattern of dinosaur diversification across the Triassic and found something unexpected. During the period when the dinosaurs and pseudosuchians were coexisting in the late Triassic, the dinosaurs were not actually outcompeting the pseudosuchians. The two groups were not locked in a competitive struggle that the dinosaurs were slowly winning. Instead, they were largely coexisting in different ecological spaces, with the pseudosuchians dominating the larger herbivore and predator niches, while the dinosaurs occupied smaller, more marginal roles. The dinosaurs did not win a competition. They survived a catastrophe. And survival, as it turns out, does not require superiority. It requires resilience. This distinction matters enormously, and not just for our understanding of prehistoric life. It matters for what it tells us about how history actually works, in biology, and perhaps in other domains as well. The winners of history are not always the strongest or the most efficient or the most impressive. They are sometimes simply the ones who are in the right place at the right moment, with the right combination of traits to endure what nothing else could endure. The dinosaurs were resilient in ways the pseudo-Suchians were not. Perhaps their physiology gave them an edge in surviving the volcanic winter that triggered the end Triassic extinction. Perhaps their geographic distribution protected some populations from the worst effects. Perhaps their somewhat smaller average body size made them less vulnerable to food shortages during the recovery period. Perhaps some combination of all of these things. What we know is that the pattern is consistent across the entire history of the dinosaurian dynasty. Dinosaurs did not rise by defeating their competitors in fair ecological combat. They rose by surviving when their competitors could not. The Great Dying cleared the path for the Archosaur radiation. The end Triassic extinction cleared the path for the dinosaurian dominance. And 66 million years ago, the asteroid that ended the reign of the non-avian dinosaurs would eventually clear the path for the mammals. Catastrophe is the engine of evolutionary opportunity, and the dinosaurs understood this better than any group of animals before or since. Now here is where the story gets stranger still. For most of the 20th century there was a scientific consensus about what kind of animals dinosaurs were. They were reptiles, large ones, unusual ones, spectacularly successful ones, but reptiles nonetheless. Cold-blooded, slow in their internal physiology, dependent on external heat sources to regulate their body temperature. Essentially giant lizards, which is exactly what the name dinosaur, terrible lizard, had always suggested. This consensus shaped everything about how we imagine the dinosaurs. The sluggish brontosaurus wading in swamps because its body was too heavy to move efficiently on land. The stegosaurus with its plates serving as solar panels to warm a body that could not generate its own heat. The tyrannosaurus as an ambush predator, waiting in cover and lunging at passing prey rather than pursuing it, because its metabolism could not sustain a prolonged chase. The general image of the Mesozoic world as a slow, hot, torpid place populated by cold-blooded giants moving through the world at half speed. And then, beginning in the 1960s and accelerating dramatically through the 1980s, 90s and 2000s, a revolution happened. The dinosaur renaissance. That is what paleontologists call it, and it changed everything. The revolution began with a paleontologist named John Ostrom, who in the 1960s described a new species of small theropod dinosaur from Montana that he called Deinonychus, which means terrible claw. Deinonychus was not enormous. It was roughly the size of a large dog, but what was extraordinary about it was not its size, it was its anatomy. Deinonychus was built for speed and agility in a way that cold-blooded reptiles simply are not. Its legs were long and slender, built for running. Its body was balanced over its hips, the classic bipedal posture of an active, fast-moving animal. Its forelimbs were equipped with 3-fingered hands bearing large curved claws, and on each foot one claw, the famous sickle claw, was enlarged and modified in a way that strongly suggested it was used as a weapon during active pursuit of prey. This was not an animal designed for slow ambush. This was an animal designed for pursuit and active predation. And active predation, the sustained pursuit of prey, requires a metabolism that can sustain high levels of physical activity for extended periods. That is a warm-blooded metabolism, or something very close to it. John Ostrom's description of Deinonychus, combined with his growing conviction that birds were directly descended from theropod dinosaurs, a connection that most scientists at the time considered absurd but which is now universally accepted, sparked a fundamental rethinking of dinosaur biology. If Deinonychus was actively pursuing prey, then many other dinosaurs were probably active in ways that cold-blooded reptiles cannot sustain. And if many other dinosaurs were that active, then dinosaurian physiology was probably not simply reptilian. The work that followed over the next several decades transformed our understanding of dinosaurs more completely than any development since the bones themselves were first recognized as belonging to a distinct and extraordinary group of animals. Bone histology, the study of the microscopic structure of bone tissue, revealed growth patterns in dinosaur bones that are fundamentally different from those of modern cold-blooded reptiles, and very similar to those of modern warm-blooded mammals and birds. Growth rings in dinosaur bones show rapid and sustained growth, not the slow and intermittent growth of reptiles. Isotopic analysis of fossilized dinosaur teeth and bones revealed chemical signatures consistent with the maintenance of relatively stable internal body temperatures, not necessarily the precise thermoregulation of a modern bird or mammal, but something considerably more sophisticated than the external temperature dependence of a modern lizard or crocodile. The feather discoveries from China and other sites, which began emerging in significant numbers in the 1990s and have continued ever since, confirmed that a substantial portion of the theropod lineage, the lineage directly ancestral to birds, was covered in insulating structures from a very early stage in its evolution. Feathers, or proto-feathers, are insulation. Insulation is what warm-blooded animals use to maintain their internal body temperatures. Cold-blooded animals do not need insulation because they are not generating body heat to conserve. Taken together, all of this evidence points toward a picture of dinosaurian physiology that is very different from the cold-blooded reptile of the mid-20th century imagination. Many, possibly most dinosaurs were running metabolisms that were considerably warmer and more active than those of modern reptiles. Some may have been essentially homeothermic, maintaining a stable internal temperature the way birds and mammals do. Others may have occupied intermediate positions on the metabolic spectrum, running warmer than a crocodile but not quite as precisely regulated as a modern hawk or wolf. The exact position of various dinosaur lineages on this metabolic spectrum is still debated, but the debate is no longer about whether dinosaurs were simply cold-blooded reptiles. That question has been settled. They were not. The debate is now about the fine details of how their physiology worked, which is a much more interesting and scientifically productive question to be asking. And here is the twist within the twist, the second layer of surprise that this new understanding reveals. If the dinosaurs were warm-blooded, or at least mesothermic, running significantly warmer than modern reptiles, then their long reign of 166 million years looks very different from the way it looked when we imagined them as cold-blooded giants. Cold-blooded animals are in many ways more vulnerable to environmental extremes than warm-blooded ones. A cold snap that drops temperatures significantly below normal can be fatal to a cold-blooded animal that cannot generate its own heat. A prolonged period of darkness and cold, such as the impact winter that followed the end Cretaceous asteroid, would have been devastating to cold-blooded animals that depended on external warmth to remain active. But warm-blooded animals can survive cold. They can maintain their body temperatures through internal heat generation, even when the external environment is cold and dark. They can remain active when cold-blooded animals are torpid. They can continue to hunt, to forage, to survive when their cold-blooded competitors are helpless. This realization has profound implications for the end Cretaceous extinction. The traditional story tells us that the dinosaurs were wiped out by the asteroid and its aftermath because they were too large, too specialized, too cold-blooded, too inflexible to survive in a world suddenly gone dark and cold. And the mammals survived because they were small and warm-blooded and lived in burrows and could eat almost anything. But if the non-avian dinosaurs were also warm-blooded, or at least significantly warmer than cold-blooded reptiles, then their inability to survive the impact winter cannot simply be attributed to cold-bloodedness. Something else must explain why the large non-avian dinosaurs died while the birds, also warm-blooded and also descendants of theropod dinosaurs, survived. The current leading hypothesis is that the difference was not about physiology alone, but about body size combined with diet combined with ecological flexibility. The large non-avian dinosaurs, the tyrannosaurs and sauropods and hadrosaurs and ceratopsians, were simply too large to survive on the drastically reduced food supply of the impact winter. They required too much food to sustain their enormous warm-blooded bodies. When the plants died and the herbivores starved and the predators followed, the large dinosaurs had nowhere to go. There was not enough food in a darkened, cooling world to sustain animals of their size. The birds survived because they were small. Small enough that seeds and insects which persisted through the impact winter were sufficient to sustain them. Small enough that they could find shelter and conserve energy. Small enough that the resources of a devastated world were adequate to keep them alive through the worst of it. The birds survived not because they were better than the other dinosaurs in some absolute sense. They survived because they were the right size at the right moment, with the right diet in a world suddenly organized around very different rules than the ones that had prevailed for the previous 166 million years. The dinosaurs were warm-blooded, or close to it, all along. The image of cold-blooded reptilian giants that dominated the popular imagination for most of the 20th century was wrong. The dinosaurs were, in their physiology and their activity levels, and their parental behaviors and their social structures, much more like large, feathered, active, energetic animals than like any modern reptile, which means that the history of life did not go from cold-blooded reptiles to warm-blooded mammals with a clean break at the Cretaceous-Paleogene boundary. The warm-bloodedness, or something very close to it, was already there, already embedded in the dinosaurian lineage, already shaping the behaviours and the ecology and the diversity that made the Mesozoic world so extraordinary. The mammals did not inherit the Earth from cold-blooded giants. They inherited it from warm-blooded ones. Now let us go even deeper. There is a third twist in this story, and it may be the most surprising of all. For decades, the story of the end Cretaceous extinction was told as a straightforward tragedy. The dinosaurs were doing wonderfully. They were thriving. Their diversity was at or near its peak. And then the asteroid came and wiped them out. A random cosmic accident, a bolt from the blue, ending the most successful dynasty of land animals the world had ever seen in a matter of days or months. But the geological and paleontological record of the late Cretaceous tells a more complicated story. In some regions, dinosaur diversity in the last few million years of the Cretaceous does appear to have been declining, not catastrophically, not even dramatically, but measurably. Some lineages that had been diverse and widespread in the Middle Cretaceous were becoming rarer by the end. Certain ecosystems show reduced dinosaur diversity in their latest Cretaceous deposits compared to earlier formations. Additionally, the Earth of the late Cretaceous was not environmentally stable. Massive volcanic eruptions, the Deccan Traps of India, were pouring enormous quantities of lava and volcanic gases into the atmosphere for hundreds of thousands of years before the asteroid struck. These eruptions were not as catastrophic as the Siberian traps of the Permian, but they were substantial. They were warming the climate and acidifying the oceans and stressing ecosystems in ways that some paleontologists believe were already putting pressure on many species before the asteroid arrived. The asteroid, in this view, did not strike a healthy and thriving world. It struck a world that was already stressed, already showing signs of ecological instability, already experiencing the early stages of what might, over a longer time scale, have developed into a significant extinction event even without the cosmic intervention. The asteroid did not single-handedly doom a flourishing dynasty. It administered a killing blow to a dynasty that was, in some regions and in some lineages, already beginning to feel the pressure of a changing world. This does not diminish the asteroid's role. The asteroid was, without question, the decisive factor. The extinction that resulted was rapid, global, and catastrophically complete in a way that no purely volcanic event would have been. Without the asteroid, many lineages of non-avian dinosaurs would almost certainly have continued. Some would probably have survived into the Paleogene and beyond, but it does complicate the simple narrative of a thriving world struck down without warning by a random cosmic accident. The truth is messier and more interesting than that. The truth is that the world of the late Cretaceous was already changing. The truth is that the dinosaurs, for all their extraordinary success over 166 million years, were encountering a world that was slowly becoming less stable. And the asteroid, arriving in the middle of this slow transformation, produced an extinction that was part cosmic accident and part the culmination of pressures that had been building for some time. History is rarely a simple story of success followed by sudden failure. It is usually a story of gradual change punctuated by moments of dramatic acceleration. The end of the dinosaurs is exactly this kind of story. And knowing this makes the survival of the birds even more remarkable. Because the birds did not just survive the asteroid. They survived the Deccan Traps. They survived the climatic instability of the late Cretaceous. They survived the gradual restructuring of ecosystems that was already underway before the asteroid arrived. They survived all of it. And they came through into the Paleogene world not merely as refugees from a catastrophe, but as a lineage that had already been tested and found resilient by a world that had been slowly testing everything. The birds were ready, not because they knew what was coming, not because they planned for it, but because the same adaptations that made them successful in the complex and changing world of the late Cretaceous, small size, dietary flexibility, the ability to exploit a wide range of food sources, high reproductive rates, were precisely the adaptations that allowed them to endure what the early Paleogene demanded. They were the right animals at the right moment, and here is the final turn of the twist, the deepest and quietest surprise of all. We began tonight by saying that the dinosaurs rose from the ashes of the Permian extinction, and this is true. The archosaurs that would give rise to the dinosaurs were among the survivors of the greatest mass extinction in the history of complex life. They inherited a nearly empty world and slowly, over tens of millions of years, filled it. But there is something recursive, something almost poetic about the full arc of the story. The lineage that would become the dinosaurs arose from catastrophe. The dinosaurs themselves achieved dominance through catastrophe, the end-Triassic extinction that cleared their competitors. The non-avian dinosaurs were ended by catastrophe, the asteroid impact, and the birds, the surviving dinosaurs, rose to dominance in the aftermath of that catastrophe, inheriting the emptied world of the early Paleogene exactly as their distant ancestors had once inherited the emptied world of the early Triassic. Catastrophe, survival, inheritance, diversification, catastrophe again, survival again, inheritance again, diversification again. The pattern repeats across hundreds of millions of years, the same fundamental cycle, playing out at different scales in different ages with different actors. As if the Earth itself has a rhythm, a deep pulse beneath the surface of events that drives life forward through crisis after crisis, each one clearing the stage for something new. The dinosaurs are not merely a chapter in this story, they are the clearest and most complete illustration of it that the fossil record has given us, and we are part of it too. The mammals that inherited the world after the end Cretaceous extinction, the lineage that eventually gave rise to humans, were among the survivors of the same catastrophe that ended the non-avian dinosaurs. Small, warm-blooded, flexible, living in the shadows and the burrows of the Mesozoic world, enduring the impact winter, emerging into the early Paleogene, and beginning their own slow and patient diversification into the rich and varied world we know today. We're not separate from the story of the dinosaurs, we are the next chapter. The mammals rose exactly as the dinosaurs rose before them. From catastrophe, through resilience, into diversity, into dominance, into a world shaped by everything that came before. And now, in this particular moment of deep time, we are the animals that can look back at the dinosaurs and understand, however partially, however imperfectly, what they were. We are the animals that can dig their bones from the earth and read the story written in their stone. We are the animals that can sit quietly in the night and tell their story to each other, in the long darkness, in the comforting warmth of shared narrative. This is what makes the rise of the dinosaurs so genuinely profound. Not just the drama of it, not just the scale of it, but the fact that it is our story too. The same forces that shaped the dinosaurian dynasty are shaping us. The same deep rhythms of catastrophe and resilience and inheritance and diversification that carried the dinosaurs through 166 million years of Earth history are carrying us forward through our own brief moment in deep time. We are the inheritors of the world the dinosaurs built and shaped and filled with their extraordinary presence for an unimaginable span of time. We breathe the air that passed through their lungs. We walk the ground that bore their footprints. We look up at the same stars they saw from their Jurassic floodplains, and their Cretaceous deserts and their polar forests. And every morning when the birds begin to sing, we are hearing the living voices of the dynasty that preceded us, the last and most tenacious representatives of the most successful land animal lineage in the history of life on this planet, still here, still singing, still carrying the story forward, note by note, dawn by dawn, season by season, across the slow and patient turning of the world. The dinosaurs rose from the ashes of catastrophe, and so, in our own way, did we. And so, perhaps, does everything that endures. Let that be the last thought before sleep finds you. Not the ending of the dinosaurs, but the pattern beneath the ending. Not the darkness of the impact winter, but the morning that eventually came after it. Not the extinction, but the survival. Not the loss, but the inheritance. The world keeps going. Life keeps going. The story keeps going. And tonight, in the quiet and the warmth, so do you. There is a kind of peace that comes from understanding how long the Earth has been here. Not from the numbers themselves, the millions and hundreds of millions that the mind cannot truly hold, but from something quieter and deeper that those numbers hint at. A sense of the world as patient, as enduring, as something that has seen catastrophe and catastrophe again, over and over, in a long and slow and ultimately generous rhythm. The Earth has been here for 4.5 billion years. Complex animal life has been here for roughly 600 million years. The dinosaurs were present for 166 million of those years, which is by any measure an extraordinary span. long enough for entire mountain ranges to rise and erode, long enough for continents to drift thousands of miles from where they started, long enough for the climate to cycle through warm periods and cool periods, and warm again, multiple times, with the slow and enormous patience of geological time. Through all of it, the dinosaurs adapted. Through all of it, they endured. And the world they lived in was not so different from the one we inhabit. At its most fundamental level, there were still seasons, still weather, still the daily rhythm of light and darkness, still morning when the world warmed and woke, and evening when it cooled and settled, still the cycle of rain and dry, still the cycle of life and death, and life again. The same sun that rose over Brachiosaurus browsing in the Jurassic canopy rises over us each morning. The same moon that hung above the late Cretaceous floodplain hangs above us still. The stars that the hadrosaur herds move beneath on their nighttime migrations are the same stars, in almost the same positions, that you could see if you stepped outside tonight and looked up. There is a continuity here that is genuinely comforting, if you allow yourself to feel it. The world is very old and very patient, and it has seen much worse than anything we face, and it has endured, and the life on it has endured, and will endure. The dinosaurs are part of that continuity. They are not gone. They are transformed. The great sauropods and the terrible tyrannosaurs and the crested hadrosaurs and the armoured ankylosaurs, those particular forms are indeed gone, and we mourn them, as one mourns anything that was once magnificent and is gone. But the lineage persists, the deep biology persists, the hollow bones and the air sacs and the warm blood and the feathers, all of it persists in every bird that ever took flight. When you listen to birdsong in the morning, you are listening to the voices of animals whose direct ancestors were present at the beginning of the dinosaurian dynasty. The call of a crow in a Cretaceous forest would not have been so different, in its fundamental nature, from the call of a crow today. The parents of small theropods in their Jurassic nests were doing something essentially similar to what the parents of sparrows do in a garden today. Life has a continuity that time cannot break. It can transform it, can reduce it, can redirect it, but it cannot break it. The rise of the dinosaurs is ultimately a story about this, about life finding a way through catastrophe and scarcity and competition and change, about a small, quick, unimportant seeming lineage of archosaurs in a red late Triassic desert, becoming, over the patient course of geological time, the most successful dynasty of large land animals the world has ever known. About endurance, about adaptability, about the stubbornness of life in the face of everything that tries to end it, and about the quiet morning when the first bird calls and the world starts over again. Close your eyes now, if they are not already closed. Let the images of the ancient world grow soft and fade. Let the red desert of the Triassic dissolve into warmth. Let the Jurassic forest settle into a gentle green haze. Let the calls of the hadrosaurs become softer and softer, fading like the last tones of a great song. The world is breathing, slowly, deeply, as it has always breathed, in and out, in the long, slow rhythm of geological time, and you are part of it. A living thread in the same fabric that once held the dinosaurs, made of the same atoms, lit by the same sun, breathing the same essential air. Rest now. Let the ancient world hold you. Let the patience of deep time carry you gently into sleep. You are safe. You are ancient. You are home. And so our journey through the Age of Reptiles and the rise of the dinosaurs comes gently to its close. We have travelled across more than 200 million years of Earth history tonight. We have stood in the red deserts of the late Triassic and watched the first tentative steps of the dinosaurian lineage. We have moved through the recovering world of the early Jurassic as the dinosaurs began their slow and patient rise. We have stood in the shadow of giants on the Jurassic floodplains. We have listened to the resonant calls of crested hadrosaurs echoing across the Cretaceous evening. We have watched the rise and fall and transformation of a dynasty that lasted longer than the human mind can truly hold. The dinosaurs remind us that life is more patient, more resilient, and more inventive than we can easily imagine. They remind us that endings are often beginnings, that even from the deepest catastrophe, something finds a way through, that the small and the quick and the adaptable sometimes inherit the world from the large and the powerful and the fixed, and they remind us that they are still here. In every bird that calls from a tree or soars on a thermal or dives into a river or sings outside your window at first light. The dynasty of the dinosaurs is not over. It never ended, it simply took wing. Thank you so much for watching. If you would like to see more videos like this, please consider leaving a like and subscribing to the channel, as it really helps us continue making more content. Anyways, see you in the next one. Now, dear traveller through deep time, let your eyes close fully, let your body settle fully into rest. Let the images of ancient worlds and ancient creatures fade gently into the warm, dark quiet behind your eyes. The story has been told. The journey is complete. All that remains is the oldest and most necessary journey of all. The journey into sleep. Let the night receive you. Let the quiet hold you. Let the long, patient breath of the earth carry you softly, gently, deeply into rest. You are safe. You are still. Good night. If you could have watched any moment from the Age of Reptiles, the first dinosaurs in the Triassic desert, the great sauropod herds of the Jurassic, or the crested hadrosaurs of the Cretaceous floodplain, which would you choose and why? Leave your answer in the comments below. Thank you so much for watching. If you'd like to see more videos like this, please consider leaving a like and subscribing to the channel, as it really helps us continue making more content. Anyways, see you in the next one.